Good morning, everybody. Welcome for this new colloquium, for the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Michael Hartmann, and he will talk about what can we expect and hope for in quantum computing. So Dr. Rainer Schwedel will introduce Michael. So Rainer.
Thank you, René. Welcome, Michael. We have Dr. Michael Hartmann today with us, and he will talk about quantum computing, which is not maybe the normal topic that we have here, but it's an upcoming technology, and it may be of great importance for us as well. So Michael will explain us a bit about what we can hope for and what is possible. So Michael Hartmann studied physics at the Ludwig-Maximilians University in Munich, and he received his PhD degree at the University of Stuttgart in 2005. After a Theodor Linnen Fellowship of the Alexander von Humboldt Foundation at Imperial College in London, Michael was awarded an Emmy Noether Fellowship of the German Research Foundation to build up a research group at Technical University Munich in 2008. That's the so-called TU. He worked then at the Heriot-Watt University of Edinburgh as an associate professor from 2013 to 2019 and spent a year at Google Quantum AI in 2019 before finally becoming a full professor at the FAU Erlangen. He currently leads the hardware-adapted theory efforts of the Munich Quantum Valley Initiative. So I'm very curious about what Michael will tell us today. So welcome, Michael, and the audience is yours now.
Yeah, thanks very much. Thanks a lot for the nice introduction and for having me. And so in this talk, I want to present a sort of current view of the status of the field of quantum computing and ask or address the question what we can expect from this or hope for if the development runs well in the next years. And this talk will be grouped in roughly 3 parts. So in the beginning, I try to explain what a quantum computer is, how it computes, and why it is so good or powerful. And then we'll talk about the main things, so which applications we can expect and hope for. And there goes through some like the main candidates. And in the end, I will try to address what is still missing in the development so that this tool becomes really useful and powerful. And so, by the way, if you have questions, please feel free to interrupt me at any time, right? So to get started, I want to talk a little bit, or say, remind you how classical computers work. So for processing information with a machine, we typically represent numbers in a binary representation. So then we only need to use 2 digits, a 0 and a 1. Yeah, and then, okay, so the 0 as we use it is represented by the binary 0 and the 1 as well by the binary 1. But as we only have 2 digits already for a number 2, we need to have a 2-digit string, and that's then 1, 0 in this notation. And then the next number is a 1, 1, and you can go on with this and actually represent every number that you use in the way you calculate yourself in such a binary representation. And this has the advantage that we only need to have 2 sort of physical states to represent these numbers. And so one example for this is that actually in a computer that runs electrically, the 1 is represented by a high voltage value or above a certain, well above a certain threshold, and the 0 is presented by a low voltage value. And this is sort of the smallest entity of information that we can think of, and that's why it's called a bit, because it's the smallest bit of information. And now to process this information, to do calculations, we need to do so-called logical operations, and these are done by transistors. So a transistor is a device where, so typically has 3 wires, and the voltage in one wire controls the voltage across the other 2. And now, okay, there has been a very significant effort in reducing these transistors in size and integrating a lot of them into a chip. And so that means that there are very many of these transistors in modern day chips. So for example, a typical smartphone has 10 billion transistors in it. And now you can do crazy numbers. You can wonder about how many transistors are there on this earth at the moment. And that's roughly 10 to the 23. So it's a number that actually reaches Avogadro's scale, right? And it becomes even more funny if you compare this to the estimated number of sand grains in all deserts and beaches and whatever. And that's actually a factor 10,000 smaller. Yeah. So semiconductor industry has perfectionized this to a degree that we have produced a lot more transistors than there are sand grains on this planet. So really, among the achievements of mankind, whether you deem it good or bad, it's an impressive one. Okay, and then, so what are these logical operations? If you represent numbers in such a binary representation, what a computation is actually that you need to find a mapping or a function that takes in such a string of input bits, zeros and ones, and produces a string of output bits. And then what makes a computer useful is that you can decompose this operation into a set of elementary steps. And it turns out you don't need many of these elementary steps, which you call logical gates, to compose what you want to do. So examples for such logical gates is a NOT, which just turns a 1 into a 0 or a 0 into a 1. Or, for example, there are also gates which process 2 bits. So an AND gate is one that only has a 1 output if both inputs were both 1 and 0 in all other cases. And then, as I said, the interesting thing is that this set of gates, or there is a small set of gates which is enough to compose every computation that you want to do. So if you can build a computer that can do these gates, it can do, in a sense, everything you want. Okay, now we want to, or for understanding quantum computing, we need to transfer this into the quantum mechanical world. So what's happening in the quantum mechanics world? Okay, so there a dynamics of an object, and I'm taking here a football to have an everyday object, is described by what we call a wave function. So this is basically a thing that associates to each position and each time some complex number. And the absolute square of this complex number will actually tell us the probability to find that object at that position at that time. And now the interesting thing is, so the dynamics of this object is then actually described by the Schrödinger equation, which I've written down here. So here we see this wave function again, and h is a quantity that actually characterizes the system that we are looking at, the forces that act on this object, and all these things. And crucially, this is a linear equation. So meaning that if I have one solution and I have a second solution, the sum of these will also be a solution for this equation. What does this mean for the objects? Right? If we know that the sum of two configurations or two physical states are also a possible physical state, what does this mean? So I've plotted here two possible of such wave functions. So this like yellow one and this green one. And then if I take the sum of both, then I get this red line. And if I look at the probability to find the object in this space, then I need to take the absolute value squared of this red line. And this is what is sketched here in this blue thing. And then you can see this has a 0 at a point where the two individual ones would not be 0, and therefore leads to an entirely new configuration. So you really need to conclude that this means that objects can be in two locations at the same time in quantum mechanics. Now, getting back to the football example, you can immediately guess this is a literal game changer. Yeah. So if both teams can score at the same time, this changes the game completely. And that's what you try to exploit in quantum computing. Now, to get a bit more specific, so in many situations, and I'll describe in a little bit when this occurs, you can, because a sum of two solutions of the Schrödinger equation is also a solution, any wave function that you want to consider, you can often represent as an expansion into a discrete set of some basis wave functions. And that's really the same thing as writing a vector in, say, 3D space as a composition of directions along the coordinate axis. Yeah, so say here you have a point in 3D space, and then this vector is just a sum of the vectors along the basis directions. And so if you have this for only 2 dimensions, yeah, say I would only have an x direction and a y direction, then I could associate a 0 to one direction and a 1 to another direction. And then I have also a physical representation of this 0 and 1, so I have a representation of a bit. And if I do this for such a quantum state, then the usual notation is this somewhat fancy brackets here. And that's why I'll use them in the further talk. And the quantum mechanical bit is then called a qubit. Yeah, so this is like a quantum system where there are sort of 2 basis states for it. And then the important observation is that if I move this point here in the 3D space, then I can do movements where all 3 coordinates change at the same time. And for a quantum computer, you can think of, okay, so this is the motion of, imagine you would not have only a 3D space, but a much higher dimensional one, and then moving the point in that space would change many more coordinates at the same time. And that's what you do in a quantum computer, and that's why it's computationally that powerful. Now, when does this situation occur that you can have this discrete basis set? That comes from energy quantization, and that's a result of the boundary conditions in like more mathematical terms, or a result of like trapping particles or physical objects to a restricted region in space. So an example is standing light wave between 2 mirrors. Yeah, so half the wavelength needs to fit an integer multiple of times in the distance between the 2 mirrors, and therefore you only have a discrete set of solutions. And the same occurs with the states of electrons in the Coulomb field of a nucleus. Yeah, so the quantization of energy levels is because you need to fit sort of the wavelengths or half the wavelengths of the wave function in a circle around this thing, an integer multiple of times. And that's made use of in ion trap quantum computers, for example. And generally, you have some potential, so a force that attracts a particle to a certain region of space. And that leads to the fact that quantum mechanical, so energy states, are wave functions that have a discrete set of nodes in this region. And then you take the 2 lowest energy ones, typically for representing your logical 0 and logical 1. But these are now quantum mechanical wave functions, and you can form these sums or superpositions of them. So in my work, I typically consider superconducting qubits as the physical system to actually implement this. And that's why I spent a few words about these. It's not the only platform on the market, and it's a very open question, which is the most promising one. Yeah? So I'm not trying to sort of say one is better than the other here, because that really only future can tell. But I'm just showing the platform that I'm most interested in. So these superconducting qubits, you can think of that they are sort of artificial atoms that are made of superconducting wires. And the easiest circuit that you can do with a superconducting wire is an electric resonance circuit. So this is just a capacitor and a coil, an inductor, forming a loop. And then the currents and charges in this thing oscillate, and actually this is nothing else than a harmonic oscillator. So a harmonic oscillator is not that useful for building a qubit, and I can say why in a second. So what you do is actually that you replace this coil, this inductor coil, by a part that is made of Josephson junctions. So Josephson junction is actually two superconducting parts of metal that are interrupted by a thin insulating layer. And the effect of this is that the distance of the energy levels, so here this you should think of like energy goes from top to from bottom to top is increasing energy. So this lower bar represents the lowest energy state of the system, and this is the next higher one. And if they are not equidistant, as in a harmonic oscillator, one can select in addressing these which transition you want to talk to. And that's why you use this nonlinear system where there are different energy differences between pairs of neighboring levels, and typically choose the lowest two states to form the qubit. And oh, sorry, wrong direction. And if you wonder how this physically looks like, so here are some pictures from, so the qubit is actually this thing here, that are produced in the quantum device lab headed by Andreas Wallraff at ETH in Zurich. And I'm using their pictures because we have some nice collaborations with them. Now, these superconducting quantum chips are also built in a much larger scale by companies or also at universities. And I'm showing here some pictures. I actually realized they're not the most up-to-date ones, so in parts a few years old, by devices from Google, IBM, and also USTC in China, which also build very large devices. And this down here where you can see a bit more, so that's a picture from a university lab. That's why they allow you to see the qubits actually and not only show you the shielding. So this is a 17 qubit chip that's been experimented with at ETH in Zurich. And so these devices have from 100 to several hundred qubits already. And then so these whole things go into a cryostat. So a cryostat is a very big refrigerator, you can say. So it's meant to cool down to about 10 millikelvin. And of course, the temperature is lower the further you go down. So this actually has a sort of cylinder shielding around it. Usually here it's open so that you can see inside, and this is all the control wires. And then, so these chips actually go down to the bottom where you have the coldest temperature. So that's how these things look like in the lab. Now, why is representing information in quantum states, why can this lead to much more powerful computing than the classical computing that we already have? So that only becomes really clear when you look at several qubits. So a single qubit, as I explained before, because the Schrödinger equation is linear and therefore sums of solutions are also a solution, can be in a superposition state where it represents the 0 and the 1 at the same time. So that is a thing that is in contrast to a classical bit, which can only be 0 or 1. So here you need to describe the state of this qubit, you need two coefficients. Yeah? How much is in 0 and how much is in 1. Now, if you take two qubits, you can form a sum of all possible configurations. So 0, 0, 0, 1, 1, 0, and 1, 1. And these, consequently, you need 4 coefficients to specify that state. Yeah? And then if I add another qubit and go to 3, then for each of these configurations for 2, I get 2 configurations. Yeah, so the 0, 0 with a 0 in front and the 0, 0 with a 1 in front. And likewise for all the other guys. So what you observe is that with each qubit that you add, the number of coefficients that you need to specify the state doubles. Yeah? And then if you think about 50 qubits, which is for industrial players a fairly small chip these days, then this 2 to the 50 coefficients that you would need to specify the whole state is actually 10 to the 15 already. And that becomes a very large number. So that's something that no longer fits into a typical RAM of a good PC that you have. And the way the quantum computer processes this information is that it's capable of changing all these coefficients at the same time. Yeah. So that's what I wanted to explain with the analogy of the point in 3D space, where if you move this point, it changes all three coordinates at the same time. Now here, if you process this quantum mechanical state through a quantum computer, that quantum computer is capable of changing all this exponential number of coefficients at the same time. And in that sense, it computes massively parallel. And if you're capable of using this cleverly, then you can gain computational power over classical computers. Okay, so how does this processing of the state occur in a quantum computer? So like in classical computing, you can actually decompose what you want to do into a set of elementary operations that we call quantum gates. So there is an input quantum state, then you apply a sequence of quantum gates to it, and in the end you need to measure these qubits. And these quantum gates, it turns out it's sufficient to have a specific set of 1 qubit gates. So these are gates or operations that change the quantum state of a single qubit only, and 2 qubit gates. So these are operations that change the state of 2 qubits, and that's why I'm using here 2 subscripts here to indicate that this wave function is one that describes 2 qubits at the same time. And these gates can be controlled, say, by the length of control pulses that you apply to the qubits, or the duration of qubit-qubit interactions that you can switch on and off. And that's how you implement these. And then the readout or the result is also different to classical computing. So if you consider a single qubit only, then it can be in this superposition of the logical 0 and logical state corresponding to a logical 0 and a logical 1. So if you measure it, you would either get a 0 or a 1, both is possible. And this occurs with probabilities that are given by this absolute value squared of these expansion coefficients. So the result of a quantum computer is not always deterministic. That depends on how you design this gate sequence and whether you can design it such that in the end only one of these coefficients is non-zero. But it can also be probabilistic, so you might need to run it multiple times and then take an average over the results or so. Yet the output, like if you read out multiple qubits, you again get a bit string just as in a classical computer, so a sequence of ones and zeros. Yeah? Good. So I hope I was somewhat able to explain how a quantum computer works and give a hint why it can be very powerful. So what can one do with that? In some sense, one needs applications where you can exploit this massive parallel processing of information that a quantum computer offers. And the most prominent example for this is Shor's algorithm. So this has become famous because it has a very significant speed up compared to the best classical algorithm that is available. And that difference in the fact that classically this is a very challenging problem is used in encryption. So whenever you send an email or use a credit card, then typically there is a so-called RSA encryption used. And that's based on the fact that it's very hard for classical computers to decompose a large number that is a product of 2 prime numbers into these prime numbers if you don't know them. Yeah. So while, okay, for say 15, all of us know that this is 3 times 5 if it's a very large number. And for a, say, 4,000 bit key, these are numbers which are 10 to the 1,000 or something like that. So really huge ones. then it's very hard to find, if you're only given this number n, to find the two primes that actually, where their product is equal to this n. And it takes in classical computing very long because you need to test enough candidates for these. Yeah? Now, in a quantum computer, there's a way to sort of test many or all candidates in parallel. And this is done by finding a period of a specific function. This has a number theory background, why this is useful. And the way the quantum computer does this is it actually generates a superposition of many of these functions and processes that superposition such that there's a destructive interference. So the likelihood that you measure the ones with the wrong period sort of is largely suppressed. And in that way, it can do this exponentially faster than a classical computer. And if you could implement this thing, then you could crack this RSA encryption. And that would change, of course, a lot of security keeping in this world. So it's a very powerful, but currently clearly out of reach. So the quantum computers that we have are far from being capable of doing these things. Nonetheless, if one wants to make sure encryption is secure over several decades, one should start thinking now about ways of making encryption secure against Shor's algorithm. Okay, so having said that, this very famous application of Shor's algorithm is still far away, it of course triggers the question, okay, so where do we have indications for this? So what can quantum computers do now, and do we have indications really that they can be more powerful than classical computers? And there have been experiments in that direction that actually demonstrated that they are more powerful in a certain sense, and these go by the name beyond classical experiments. And what the goal of this is that you want to run a sort of well-defined computation on a quantum computer that a classical computer can no longer run, or at least not in a time that you could tolerate. Yeah. So you should think about a sort of sports competition between two computers, and whoever finishes earlier, or maybe you don't even want to wait for the second one to come into the finish line, has won this competition. And a computational problem that quantum computers are good at, and which turns out to be very challenging for classical computers, is to sample from the output of a random gate sequence. So basically in this graphical representation of a quantum algorithm that is just a sequence of gates that the quantum computer runs, you choose these gates randomly, yeah, and then apply them, and you run this very often, the same gate sequence, but an arbitrary one, and measure the output. And each output will be one bit string. So if you run this very often and repeat it many times, then you get a distribution of bit strings. And that's what I mean by saying sampling from the output. Yeah. For a 50-qubit quantum computer, there are 10 to the 15 possible bit strings. So you won't have a chance to measure all of them. But you can draw a sample. Yeah? And that's what you do. And this is what was, for example, done in this quite prominent experiment from Google in 2019. That this was the first experiment that ran such a gate sequence where the classical computer could not predict the output. Yeah? And so by then there were sort of estimates that a classical computer would need millions of years for the largest gate sequence. So there have been improvements on the classical algorithms since then, and this number has come down tremendously. But there have also been new quantum experiments where even larger discrepancies are expected. And have so far not been classical algorithms which brought this down significantly for the newer experiments. So what this experiment tells us is that, okay, so this quantum computer can run gate sequences or produce outputs that you cannot produce with a classical computer. However, okay, so this number here on the vertical axis is something like similar to a success probability, and you can see, so this is in the percent range, and actually for the large secrets, only less than 1% of all runs run correctly. So there are still too many errors to make this useful. And also that application of this random gate sequence is just a mere sports thing. So it doesn't have the ambition to be anything useful in an application. Yeah. Okay, so the natural question is which applications are actually possible, or which areas of applications are suitable for quantum computers. And I should maybe say that at this point in time, there is no useful application where a quantum computer is more powerful than a classical computer. So this has not been demonstrated. By useful, I'm thinking of an application where people would be interested in the result without being interested in whether a quantum computer has done it or a classical computer, right? So in physics science, there are things which probably classically are not computable, but these are mostly interesting because they show the power of quantum computers. Somebody only interested in the result would not necessarily care. Okay, and one of the probably most promising directions to use quantum computers is actually in quantum chemistry and also material development. Yeah, and the reason for this is that chemical reactions are quantum processes. So you need to solve Schrödinger's equation, and that's why they are well suited for running this on a quantum computer. So it's actually the natural application in some sense. And for example, in chemistry, if there are many orbitals involved, then this gives rise to a very high dimensional Hilbert space, and that means it's a classically hard problem. So it's naturally suited for the quantum computer, but also classically hard. And I mean, so and at this point, I'd also like to mention one result from my group. So we actually applied or developed a quantum algorithm for finding stable configurations of a metal chelating agent molecule. So this is something that has applications in like water softeners, catalysts, and antioxidants. So it's something that is really relevant to industry. And this was also a project done together with BASF, so the big chemistry company in Germany. And it's a type of molecule here that has strong correlation. So it's expected to be hard for classical methods. And then what we did is develop a quantum algorithm that was actually then run on a quantum computer at the University in Innsbruck in Austria, and also used some classical post-processing of the readout from the quantum computer and error mitigation techniques. And that allowed us to reach chemical accuracy. So that's an accuracy goal that you want to have in chemistry applications. Now, this was a toy-sized problem, so it's one that is still classically solvable. So as I said before, there's no application of quantum computers yet that would go beyond these classical solvable things in that sense here. Okay. Now here's a use case example or something that of the category what we hope to do with quantum computers in a more distant future. And this example is actually production of fertilizers. So the most famous chemical process in this is the so-called Haber-Bosch process. Yeah. So this fixes nitrogen with hydrogen to actually produce ammoniac. Yeah. So here's a picture of one of the first reactors where this has been done in industry. And the industrial process actually runs at about 100 bar and 400 to 500 degrees Celsius. And of course, that causes a huge energy consumption. And that energy consumption is actually about 2% of the whole global energy consumption. And at least pre-Ukraine war, it also consumed about 5% of the gas consumption, the global one. On the other hand, this same process occurs in nature. And there, of course, it occurs at ambient conditions. But we are currently not capable of reproducing this much more energy efficient process on an industrial scale. And one reason might be that we are not able to sort of analyze chemical processes, or because we cannot fully simulate them numerically. And therefore, a quantum computer, by boosting like our capabilities on which scale we can do this, may be helpful in finding new ways for actually doing this nitrogen fixation much more energy efficiently. And that would, of course, have a significant impact. Now, as for Shor's algorithm, this is something that needs many more gates than we can currently run, and is, in that sense, a hope for the future. Let me say a few words about using quantum computing in artificial intelligence. So that has triggered a huge interest. Of course, remembering that a quantum computer can process exponential amounts of data, you're tempted to think, oh, this is sort of an ideal application for it. And maybe it's something, or there's also a reason to believe that it's more robust against errors than other computations. Yeah, so often in AI applications, there's now also computations done with single-digit precision only. However, for quantum computing, there's a so-called, it goes by the name QRAM problem. And that's linked to the fact that we currently don't have an efficient way or algorithm to load classical data into a quantum computer. And why is that so? So a quantum computer, if you just think about the clock speed, is much slower than a classical computer. So for superconducting processes, and these are of the technologies that are currently on the market, the fastest ones, a single gate takes about 1 microsecond. Now, if you take a PC that has a 5 gigahertz processor, this means a single gate, classical gate, takes about 10 to the minus 10 seconds. Yeah, so it's a factor 10,000 faster. This means like the power of the quantum computer is really in this parallel processing and not in the clock speed. However, at the interface to the classical world, when you read in data, you cannot make use of this quantum parallelism, because in the classical world, you need to touch each piece of data individually. Yeah, and that's why like read-in is a huge bottleneck in this. And for sort of AI applications, one needs to think more into the direction of generative neural networks, because these can be possibly more expressive, because Hilbert space is very large, and this fact that Hilbert space is very large can also be, for example, exploited in sort of feature, what is called feature maps. Yeah. Another direction where data analysis with quantum computers becomes important is to analyze the output data of quantum computers. And already by now, and these beyond classical experiments, for example, show this, the output states of quantum computers are becoming too complex to analyze them classically. Yeah. So if an output state consists of like 10 to the 15 complex amplitudes, that's a really tremendous amount of data. So you could think of, okay, let me use like quantum neural networks to extract information of this output state, in a sense that I don't need to do that many measurements as if I would measure this output directly. And this is also something that we have worked on. In this example, it actually classifies whether a quantum state is out of a specific quantum phase of matter or not. And this was a a nice collaboration with the team at ETH in Zurich, where they actually also demonstrated this on a chip, on their processor. So looking at these things, where are we at the moment and what's still missing? So on the one hand, there are these beyond classical experiments that can run gate sequences that classical computers can't simulate anymore. And even though there are improvements on the classical algorithms, the development goes like this. So there's clearly a win of the quantum computers. However, these specific experiments don't have an application. They just run a arbitrarily chosen gate sequence. And the precision of the output is not good enough at gate sequences of this depth to use it in applications. So what do you have on the application side? There are some so-called quantum simulations. That's when you use a quantum computer to emulate another quantum system. And in that direction, progress is quite far, and this is very promising, but it only works in specific cases. Yeah. And then for algorithms, there are proof of concept demonstrations in experiments, but often these are at a size still that can be solved classically as well, and in many cases even on just a laptop. So the main challenge is that the precision of the gates is not good enough to run enough gates so that you can do, for example, Shor's algorithm, or try thinking about simulating this Haber-Bosch process. So a conclusion we need to draw is that quantum computers have too many errors still. So we need to do something about these errors. One thing is that making the gates, so improving how you implement the gates on the devices that you work on, that will help, but it's unrealistic that we can achieve a precision that is good enough for the applications that we have in mind. So the solution to this problem is quantum error correction. And how does this work? So you actually don't use one single physical qubit to encode a 0 or a 1, so a logical bit of information, but you use many physical qubits. And if you use many, of course, this requires building really large quantum processors, and that's why it will still take some time to implement this successfully or at a scale that we need. Yeah? However, the working principle has successfully been demonstrated. And I quote just two results. So one is again from the Zurich team that was achieved in 2022. And the probably most successful demonstration to date is came out early this year from Google. So you can see here, this is a larger chip than this one. And the important thing is that the error rate goes down from this red line down to this blue line. And the difference between these is that here you use less physical qubits to represent one logical one, and here you use more. So they have successfully demonstrated that adding more qubits together and using them together to represent a logical qubit improves, reduces the error rate. So the direction that this goes is the right one. You just need to make it bigger. The just is not an easy challenge. And to explain this, I want to get a little bit into how this error correction works on a very simple example. And as for the general story, I start with classical error correction. So there you also use such ideas. And the simplest that you can use, for example, is that instead of taking a single 0 and a single 1 to represent a bit of information, you use 3 zeros and 3 1s. And then if an error happens, say for the 3 1s here, so that one bit flips, say the last one goes from 1 to 0, you can still take a majority vote and say, if it's 1 1 0, it should actually be a 1 1 1 and correct the last qubits. Now you can also try this for quantum, for for quantum bits. So instead of, now things are quantum and I use these fancy brackets here, yeah? Instead of a single 0 or a single 1, I use 0, 0, 0 and 1, 1, 1. And again, if an error happens, say now I'm taking another example, so the middle bit flipped, the middle qubit flipped, I can still take a majority vote and recover that the actual state should have been this one. But in quantum mechanics, things are more complicated. And the problem is the following. So we have more types of errors. And you can see this when thinking about that such a superposition of two states is also a state. And then there can be what we call a phase flip, so that this plus sign changes into a minus sign. That's a different state. It's also an orthogonal state to the previous one, but none of these majority vote procedures would actually detect that an error has occurred here. Yeah, so there is, in quantum mechanics, there's not only a bit flip error, there's also a phase error. So you need to do something more involved to detect and correct these errors. But that can be done. And you need to do this by measuring actually correlations of 4 qubits. And a consequence of that is it requires many physical qubits per logical qubit. Yeah, so if I flip back, you can see here, so each of these dots is a physical qubit. I think these are like 100 that represent just one logical qubit. And so why do we need so many? Well, there can also be events where not just a single error happens, but two. Yeah. And if I think of two like qubit flips here on this 111 state that happen simultaneously, it brings this to a 100. Now, if I do now a majority vote, I would guess that the correct thing is actually a 000, which is of course not the 111 where I came from. However, if I use instead of 3 qubits, 5, and 2 of them flip, I can still take like a majority vote and recover the correct 111. Now, taking this to the full quantum scale, we actually have currently predictions that we'll need between 1 and 10,000 physical qubits for one logical qubit. And this means a useful quantum computer needs about 1 million physical qubits and very good control over these. Yeah? So even with the, I would say, impressive achievements that are around these days, that there are chips with about 1,000 qubits or so, it still means there's a long way to go to this really powerful machines that can then do things like Shor's algorithm or solve problems that currently we can't even think of attacking them. So this brings me actually to a concluding statement that I want to make. In my view, quantum computers are very promising. So we are now able to do things that probably 5 years ago, or say a bit more, a lot of people in the field would have said this will never be possible or achievable. And there are already like experimental confirmations that are very powerful, but there are still problems to solve, in my opinion. So one could, of course, also wonder, is it just a scaling effort that you need to make things bigger? I think it will require solving certain technical problems to make quantum computers at a scale that makes them really useful. And with that, I'm done. I thank you for listening. And if you want to see more on what we are doing in my group, there are these 2 QR codes to our group page and LinkedIn channel, which should give a bit more of information. Thanks very much.
Well, thank you, Miguel. Thank you very much, Michael. I have enjoyed the talk very much. It has given, I think, a very good and realistic impression also of what's going on right now in the field. Now it's time for questions and answers. Please raise your digital hands. I give you time to think. I have a question, of course. Let me see. Yes.
Yeah.
Jorge, maybe switch on your camera when you ask, so it's easier for me to identify you.
Hello. Can I?
Yes, yes, yes.
Okay.
We can hear you. We can see you.
Okay. Thank you very much, Michael, for a very nice talk and a smooth introduction for laymen, both on the basics and on the problems of the current technology. However, I feel I miss something of something technical, so to say. I do not fully understand how all these so many qubits are managed in practice. So I understand that one bit can be set up with high voltage and low voltage, and this is not so clear when you have 10 to the 15 possibilities. How are you governing physically that you are specifying one qubit or the other?
Okay. So good. This answer is, of course, the answer to this is, of course, depends on which platform we would talk about, right? And I will now answer it for the superconducting platform because I've mentioned this one in the talk. So let me see if I have. So basically, the thing is that yeah, okay. Maybe so I don't know how well one can see this here, but so on this one you can sort of spot that there is a grid, and there are, say, per each of these square, I don't know precise. I think each of these crosses here is one. This like cyan color crosses is one qubit, and then each of these qubits has two control lines. So there is maybe if I go back one further. Look at this circuit here. There are two things how you can control this. One is to this top end, you can apply a voltage. So that would typically mean that there is a capacitance to another wire that then goes to the control stack. And this thing here is what is also known as a DC squid. So this is something that in a different field of magnetometry, so where is a highly sensitive magnetometer. Yeah.
Okay.
So meaning that if you send a magnetic field through this loop here, then you can change the properties of this. So there would be another wire here close to it through which you send a current, and that magnetic field goes in this loop, and then in this you can with this you can control this qubit as well. So then yeah, and all these signals like this voltage or current that generates the magnetic field or the applied voltage, that also all need to come through these wires, and there's a lot of technology in that you need to attenuate as well, because you go from room temperature down to 10 millikelvin. So I mean, it's not an easy task. But maybe the important thing is, because you mentioned this exponential number, is so the number of control wires is proportional to the number of qubits. So in this case, 2 per qubit. But the number of complex amplitudes that I need to specify the state, that's exponential in the number. So for 50 qubits, I need 100 control wires. And of course, I need to wonder how I get them to the qubit. And there's a lot of technical challenges there. But these 100 control wires, if I have enough precision in the control, allow me to manage the evolution or control the evolution of 10 to the 15 complex amplitudes.
Not bad. Yeah. Impressive. Yeah.
But okay, so maybe in this what you call impressive, there's also a reason why the precision of running gates on physical qubits is by far not enough to really run applications, and why we need to build this huge error correction overhead. And then, okay, thinking forward, if you want 1 million physical qubits, that means 2 million of these cables, right? So there is also a significant technical challenge, which, okay, I'm not an expert in that, but I think everyone can guess that this is not an easy thing, right? And so I think currently, I don't know what the largest qubit numbers are, but maybe 2,000 or something like that.
Okay.
So that's where things are.
And I have another curiosity, if I may, to mention. It is also technical because I know that some colleagues of mine, I work with light polarization, okay? And some colleagues of mine are working on the usage of the polarization of light for quantum computing. Could you tell us just few words on that?
Okay, so I can say a few things, but since I don't directly work with this, it's a bit limited what I can tell.
No problem. I understand.
Storing quantum information in photons is attractive because so photons keep their coherence for a long time, right? So a light pulse is very little perturbed by the environment and so on. So that's a huge advantage. Now, the challenge with photons is making logical gates in the way that I describe it here. That would require you that you generate some interaction between one photon and another photon. And so naturally, photons don't interact with each other. So you need to sort of build some, if you want to go that way, you need to build some like polaritons by sending them through some media and exploit like the interaction in the medium to have some like Kerr type nonlinear process or so.
Okay.
So the other thing is there is a way to actually do quantum information processing with just linear optical elements. But that requires that you have really single photon pulses as an input. So really non-classical pulses. And so this is, there are companies working on this approach, and probably so there's one very successful effort in China, also I think at USTC, at least one, there are probably several. And then a company that is quite well known for this is PsiQuantum. So they are in the US, in the Bay Area, and also in Australia, because the founders are originally from Australia and have now, I think, received a very substantial chunk of money from the Australian government to build up. But I cannot really comment on how mature this is because they are not very open in saying that. Yeah.
Thank you very much.
Thank you, Jose Carlos. More questions? I'm sure there must be. Or do you know everything? If not, I ask. Yes.
Sorry.
Please. Yes, please.
Well, first of all, thank you very much for such an interesting talk, Professor. But I have two doubts or curiosities. The first one is that has it been determined that qubits based on the squeeze are more stable, I think, than based on ion traps. So I don't know if sorry?
The question is, okay, so I think the question that you want to ask is, so of course you want stable qubits, but then stable, the time that they remain stable, you want to compare to how long it takes to make a gate.
Okay. You mean the decoherence time, right?
Yeah. So how many gates can you fit into a decoherence time? Okay, and All right, so the question which system is better is a very difficult one. So for ions, I think the coherence times are actually better, and they have a big advantage. So ion trap systems, and also there are platforms that work with neutral atoms. They trap them with light tweezers. So the thing is that in these technologies you can move the ions or the atoms. And that means you can do gate operations between two atoms or ions at any location, because you can just move them to a zone where you do the gate and then move them back. And that actually works well. So that has been demonstrated. And currently, I would say these neutral atom platforms actually can do more advanced. Okay, so they can run larger algorithms than the superconducting platform can. Now, the other thing is, for this error correction, one needs to measure the qubits to obtain information of whether an error has occurred, and apply a feedback on that. And the measurement process in ion traps and these neutral atom things is a lot slower and more destructive. So that's why for the superconducting devices, there have been these demonstrations of error correction that I've shown. And the same has not been achieved for ion traps or neutral atoms. So for ion traps, there have been other types of error correction. But specifically for the neutral atom platform, which in terms of algorithms that they can do is really impressive at the moment, there has not been an error correction cycle in the sense that they could do a readout, the feedback, and continue processing with the same qubits. So it's really, I think, every platform has their strengths and weaknesses, and future needs to tell which is better. Yeah.
Okay. Yeah. Thanks. And the other question is regarding with the software itself. I mean that it's important that to create a quantum computer for sure, but the development of the software I think is more advanced than the hardware. I think that there is a kind of codes or protocols more standardized for algorithm generation, or what kind of software are usually used for the development of that algorithm?
Okay, so in terms of software, there are several. Okay, there is development, and I think what is probably most widely used is what IBM provides. Is called Qiskit. Yeah. Now, you mentioned algorithm development, so okay, I'm not completely sure I understand. Because in my view, like, okay, an algorithm is more like a mathematical idea that you have.
Yeah.
And then, of course, you need to code it in a software.
Exactly. So I think that the algorithm, that the concept itself, many people know what they want to do, but to translate to a code for a classical computer and then to a quantum computer, I think there's to translate from the classical computer code to a quantum computer code. So,
okay, so you can do this. So for every, I mean, okay, on a conceptual level, you can show that for every classical Boolean circuit, you can develop a quantum circuit that solves the same problem. In practice, I think it's not it's not a useful thing to do, because really quantum computers work very differently to classical computers, and also the expectation is they are really special purpose devices, right? So, and you would never use like a quantum computer on its own. So it's really like more a coprocessor that can help to make computing for specific problems a lot better, or a lot more powerful. And to make useful quantum algorithms, you really need to have ideas how to exploit this superposition that is available in quantum mechanics and not available classically, how to make use of that for designing an algorithm that can be faster than a classical algorithm. And that also seems to be highly non-trivial, because it's actually, if one is completely honest, the field lacks algorithms. So there is Shor's algorithm, which it is known that is exponentially faster. So sort of the speed up grows exponentially in the size of the numbers that you want to process compared to the best known classical algorithm.
Mhm.
But so for many of these applications that are envisioned, there is not an algorithm where you can really prove that it's exponentially faster or have very, very solid indications, right? So this is probably also a reason why companies who would be potential interested users are still a bit cautious in investing into this, because they would like a clear evidence that, say, this chemical production process, we can analyze it a lot better. And that's not yet really there. It's just, we understand that simulating these chemistry problems is classically very hard because they are quantum mechanical problems. So it's
Yeah.
natural to expect that the quantum computer would be good there, but really having an algorithm where you can say, oh, with that input size, it's going to be exponentially faster, that's not there in this clear form. Yeah.
Okay. Thank you very much.
Yeah. You're welcome.
To follow this up, because this goes right along what I wanted to ask. So basically, okay, this may be a very, very general question, but would it be possible to, so basically you have to develop a specific, for example, let's take chemistry to be, so if I want to simulate how to create different molecules, or whether different molecules are even viable, can exist, let's put it that way, it's an easier question, I would have to devise an extra algorithm for each case, or is it possible to envisage like a more general algorithm that would solve me all kinds of molecules?
No, you would not need to do a new algorithm for each case.
Okay.
But what the algorithm would be is, okay, for a ground state of, so the lowest energy configuration of the electrons in that, for this set of orbitals with these interactions and so on.
Okay, thank you.
But that's what you would do. Yeah.
Is there any other question? People are getting hungry. So I would like you to finish with one more thing. I think this has been extremely interesting also because one reads a lot in the press, and now I have at least I think I have a much better grip on what's actually going on, and where this could be helped and where this is going. So but as a last statement, maybe, so we have heard Shor's algorithm is interesting, and maybe in chemistry, but a lot of money is going into this. So what's your sales pitch? I mean, what would you, forget about being the cautious physicist now, you say you want $1 billion for your group now, for your own company. What would you give as a sales pitch to develop this technique? I mean, there must be some kind of holy grail around there.
Yes, so I expect that quantum computing will become useful for these material science and chemistry problems. And okay, I can't give you a like McKinsey estimate for the market value of that at the moment.
No, just.
But I'm sure it has a number of billions. And if, say, it is possible to make things like a Haber-Bosch process much more energy efficient, it can also do good things for the planet. And as a country or as an economic region, I would not want to run the risk that there is in 15 years a powerful quantum computer in China, and we don't have it. And I think this can be, so if an area in the world has a superior technology that can have that impact, one can sustain this for maybe 5 or 10 years, but then you start to feel the damage.
Yeah.
And, yeah.
Okay. Yes, that is convincing. So thanks a lot, Michael. Thank you very much. Yeah, it's getting late. So thank you very much for being with us. And yeah, thanks a lot.
Thank you very much. It's been a pleasure and very interesting discussion.
Thank you. Thank you very much.
Bye.
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 Thank you. Thank you.
Thanks. Okay.
Okay. Yeah, sorry, has been a bit low participation today. I think that is because of this PhD days that were scheduled on short term right into this